Okay, this is week number 3 of the Bioengineering 599J weekly seminar on bioengineering. And today I have the special pleasure to introduce today's speaker, Mr. Don Baker, who used to be research associate professor in bioengineering, retired, and then left bioengineering. He was an ATL founder as well. And let me give you a brief introduction to Mr. Baker. He was born in Skagway, Alaska, and then he served 4 years during the Korean War in Air Force, working on airborne radar fire control system. And then he got BSEE from the electrical engineering department here in 1960 while working as an engineer for Dr. Rushmore. And he joined the cardiovascular instrumentation development program headed by Dr. Rushmore in 1958 while he was a student. So those of you who are students, you can work and you can kind of work for your degree as well. And his first project was an ultrasound dimension measuring device for sensing the left ventricular diameter in experimental animals. And he went on to become principal investigator on ultrasound instrumentation development program project that was funded by NIH. And he headed a team of engineers, technicians, and clinical collaborators whose development ranged from transit time flow meters and computers for basic physiological research on experimental animals to clinical type instruments, including the continuous wave Dopplers, the pulsed Doppler, Duplex Scanners, real-time imaging system, and color flow imaging. And in bioengineering chair's office, we have a couple of those devices in display. He authored over 200 articles and book chapters on ultrasound instruments and their principles and applications, and he also owns a number of patents. Both of his original continuous wave Doppler and pulsed Doppler have been exhibited in the Smithsonian Museum of American Medical History. In 1973 and 74, he initiated and managed the technology transfer process from the University of Washington, which launched ATL, Advanced Technology Laboratory, into clinical ultrasound business. And I was wondering what kind of the process we had at UW at that time. So he had to probably pioneer a lot of things and kind of develop the trail on his own. We know what it's like today. And, and he retired from the UW as a research associate professor of bioengineering in 1979. And he became a full-time consultant to ATL and traveled the world for the Script medical systems, teaching and conducting seminars on Doppler blood flow and imaging method on clinical cardiovascular diagnosis. He received the Pioneer Award from the American Institute of Ultrasound in Medicine in 1987, and he received the Pioneer Award from the Society of Vascular Technology in 2000. He retired from the ultrasound field in 1984, and he is enjoying the retirement life, but he's still busy working on some new ideas and etc. So it's my pleasure to introduce Mr. Baker, who will give us a presentation with the title of The Origins and Development of Ultrasound Blood Flow Detection and Imaging Method at UW from Concept to Worldwide Clinical Use. Done.
Thank you, Professor Kim. Welcome to all of you. It's a pleasure to return to the campus, although I do come now and then to visit friends and so on. It's hard to believe that I was here as a student almost 42 years ago. Time seems to pass, but the mind still goes on. I'd like to particularly thank Howard Chizek, Chairman of Electrical Engineering, and Jocelyn Kill, as well as Yeoman Kim, for their invitation and meetings that we've had to discuss involvement with the seminar. I'd like to kind of set the stage for this seminar by kind of talking a little bit about what things were really like in the early days, because what you're going to have an opportunity to hear about in a very capsule way, and it kind of quick too, because my problem is that as I go along, I'll remember something and I'll want to go off and tell a little story, but certainly time isn't going to allow that. But I started here as a student in '55 when I was discharged from the Air Force, having spent 2 years in the Arctic and 1 year at the Air Force Cambridge Research Center, where I, interestingly enough, worked on a pulse Doppler project on an airborne bomber where we were listening to the Doppler signals of the return echo to try to detect aircraft flying below us in the ground clutter. I didn't know that Doppler would become a large part of my life at that time. But anyway, coming back to the university, my own interests were to go into, originally, mechanical engineering and industrial design. I was very interested in automotive car design and things like that. But then decided, well, electronics and automation control might be more interesting. And started into electrical engineering, and I was in a class with Wayne Quinton, who you know the name, Quinton Instruments, and one day Wayne asked me, he says, "Are you working?" I said, "Well, no, I'm not doing anything at the moment." I'd worked on a project with John Fluke to instrument the reactor in chemical engineering, the first reactor on campus, and designing a control system to put a probe through the core. Anyway, I said, "Well, no, I'm not working, but I might be interested." So he arranged for me to have an interview with Dr. Reshmer. And that was the beginning of that interaction, which was about 1958. Well, to go back to the state of physiology at the time, you have to picture this because you have so many resources available now. When I think at that time, most cardiovascular research was done on the anesthetized open chest animal. And a lot of the understandings of cardiovascular function were based on that model. Reshmer had been at USC. He was actually trained as a pediatrician and decided he didn't want to get up in the middle of the night to be a pediatrician. And I don't know how he ended up at USC, but he was at USC, I think, in crash injuries or something like that. He came to the University of Washington in Department of Physiology and decided that something ought to change, that we need to develop a better understanding of cardiovascular function under better circumstances. So at the time then, there were no tools available for doing this kind of work. And so that means no resources, no laboratory, no engineers, come in sort of empty-handed and set out goals and objectives. So that was the beginning state. And somehow out of that, and while this is a summary of really what was defined as the objective, his stated purpose in life was to characterize the cardiovascular system in terms, in engineering terms, in the intact, unanesthetized animal. But no means to carry this out. So that was sort of the beginning vision that we all were introduced to. Now, I picked a line here from Paul Harvey, and I presented a seminar similar to this in Orlando about 2 summers ago to the Society of Vascular Technologists, and they're working with this equipment all the time, and I said, I bet you don't really know how this happened. And so I want to give you a little background of things you would not find or learn if you went to the library and wanted to research what happened in the field, because it's not there. What you'll find are the papers that were published on various milestones and so on. So we go from there. This is the rest of the story. So what happened? Why did it happen, and when did it happen? And that's sort of the message that I would like to get across. And in the early days, out of this activity of a question's been posed and trying to figure out ways to approach the problem, there was a period of goal setting, objective setting, recruiting engineers and others who Rushmore knew that he could not do it himself. And he had a way of attracting good people who he posed the problem and he turned them loose, basically. And he would come back. You could go and ask him if you had a problem, but basically he wasn't going to look over your shoulder. Established facilities and so on. And the program was instrument hardware oriented because I think in those days medical research was carried on in a little bit the same way that wars are fought. Wars are fought according to the weapons you have. And the rules of the game will be according to the weapons you have. I think a lot of research is the very same way. If you have tools that nobody else have, you can create a new game that nobody else can play. The fundamental variables, though, that we were aiming at were cardiovascular dimensions, pressures, and flows. This started in a very simple-minded way. Here are some examples of simple transducers that were being developed in the early 50s. A linear sort of dimension gauge here, which was no more than a rubber tube filled with mercury with a needle at each end as an electrode, and as you pulled it, it changed the cross-section area, the resistance changed. Here we see a cross-section of an ultrasonic crystal made of barium titanate. Now, you have to realize that the ultrasound at this time, the transducers were still quartz in the mid-50s, which required high voltages, were not really safe to be used on an animal. And so it was the development of the barium titanates, lead zirconate titanates, and so on in the middle and late 50s that made it possible to do some of the things that we're doing. So there's a certain aspect of these developments which are dependent on other technological developments, and that was a key one when we come to the continuous wave Doppler. Another simple device, a little mutual inductance transformer, which could be put around the vessel. Now, here are some examples of how these might be used. They were installed in animals under sterile surgery, in the open heart in many cases. Animals were allowed to recover, and then they were brought to a room where we had recording equipment and various experiments could be run. Now, the first project I had as a student was developing this device here, which measured the transit time of sound across the diameter of the ventricle. And while in retrospect it was a fairly straightforward project, it was still a learning exercise. Now here is a picture of an animal heart with a pressure gauge on here. Now this pressure gauge was developed by Wayne Quinton. He was the head of the medical instrument shop at the time. And the two major contributions that Wayne made to this activity was this pressure gauge, which was a linear variable differential transformer gauge, and it's only about so long, and the treadmill. And Quinton Instruments went on to be one of their major products was the treadmill. Well, the first treadmill was done for Rushmore to do the exercise and so on in the animal lab. Now, as we learned more and as the team built up, we went on to more and more sophisticated instruments. This example here, we see the diameter gauge. And Dean Franklin was an important person in the early history of this, along with another engineer, Dick Ellis. Now, many of the early engineers in Rushmore's program actually were military people like myself who had learned electronics in the service. And Dick Ellis was a sonar person from the Navy. He went on to become an engineer for Honeywell. Honeywell has a laboratory here, as you know, and in sonar. So Dick and Dean Franklin, of course, did a lot of brainstorming and so on, and that's really the thrust of the ultrasound, I would have to say, came from them. And this was underway when I joined the program in '58. Now this flow meter here, called a transit time flow meter, was a cuff that would place around the vessel and measured the transit time of a 5 megahertz pulse of sound from diagonally across the vessel. So the difference in time is proportional to the flow velocity, which at the root of the aorta, one number I do remember is a 2 nanosecond difference in time. Now, you have to remember, at this time, Tektronix was just coming out with the first high-speed oscilloscopes. We could not observe this effect on any of their best oscilloscopes. All you could see was a little blurring of the trace. So in retrospect, what we did, we developed an instrument where the instrument itself was the test device, because it was built purely on faith that in principle it would work. It did work, and we went on to make it work, as you can see in some of the recordings here. Well, things continue to evolve. No digital computers, no A to D converters in these days, everything analog. I don't know if any of you would ever recall the Philbrick operational analog amplifiers of the late 50s. Well, differentiators, multipliers, and things like that were all done with analog devices. And so here's an example of a typical Rushmer designed experiment with analog outputs and recording under a variety of conditions, rest, exercise, and so on. Now, one of the things I contributed to after the sonar device for the measuring left ventricular diameter was a multi-channel transit time flow meter. And here you see an 8-channel system. This opened up the possibility of doing flow distribution. And this led to studies of shock and so on, of flow distribution, and in the early 60s. A lot of this activity took place down in the health sciences, or most of it initially. This is room G212 in the health sciences building as it looked back in the late 50s. And all the racks of equipment, analog tape recorders, and these are transit time flow meters. Rushmer allowed us to be engineers. And here you see packaging, the things that would happen. Experiments would start early in the morning and go way into the night, and half of the time would be debugging a breadboard while it was connected to an animal. So things like redundancy, reliability, we're able to repair things and so on as we'd go along, because once you anesthetize an animal and got 5 or 6 people going, there was really no turning back, and you wanted to get the most out of it. So we developed packaging systems and so on, and probably did more than anybody would have ever thought you'd ever find in a lab like this. But in any event, in the room you can see hanging down a cable, and right here, it's very hard to see, is the harness, a saddle-shaped harness that was placed on the back of the animal. So the animal was prepared with the transducers implanted in surgery, and then after a few days recovery would be brought to the room, and wires were brought out through the back here, attached to this. And then whatever experiment was designed, whether it was resting, sleeping, drugs, neurological, there was all kinds of things. Well, what happened? We started to collect so much information that nobody has ever seen before that people started to rethink, how does all this really work? And this led to Rushmer's well-known book on cardiovascular dynamics, which was published in 1961. Now, it's not the definitive treatise on all of this, but it had in it a lot of the recordings and so on, which we had done. Well, how did this come about? Who was involved and so on? And we find that it's not possible for any 1, 2, or 3 to do something like this. And so we had evolved, and this process were the beginnings of the collaboration that continues still today. The interaction and working together in a team thing of a lot of different disciplines. And we find, as you can read there very easily, all the different kinds of people. And about at the same time, in the early days, late 60s, early 60s, the cardiovascular postdoctoral training program started. And there are many of those people around the world that are still in touch with, some actually, who provided a cadre of very enthusiastic, interested physicians and cardiologists, physiologists who wanted to interact and be involved. So when a new instrument was ready to go, you often had a postdoc sitting there, I want to try it, because they saw that fame and fortune, conceivably, when they got a new tool, they could publish things that nobody else could. And that's what actually happened. And some of the first 3 people that I happen to think of the names here, Robert Van Sitters, who became dean, Gene Stradness, who's a vascular surgeon, and Warren Guntherhoff were in the first set of postdocs. And they all worked through this process. And Gene Stradness became our first collaborator for peripheral vascular applications. In the early 60s, there became a shift in focus from animal-oriented research people. And the reason that happened, well, it's complicated, and I don't want to go into the details, but Van Sitters, meanwhile, had gone to Scripps Cardiovascular Institute in La Jolla. And Dean Franklin decided he didn't have a future here at the University of Washington. And he joined Van in La Jolla. And he had a lot of ideas about instrumentation and so on. He was like a child. He just kept coming out more and more. And before he left, in the late 50s, a demonstration project was done for the continuous wave Doppler. And I happened to get involved with this, and that was one of the first things I got involved with when I first came. But even though we had many types of flow meters, we were always looking for a better one, a simpler one, or so on. And the Doppler was a potential idea that could be applied in animals that was very simple. I don't know that Dean ever realized or saw the potential of this as far as clinical medicine is concerned. But he went off to La Jolla and with a NASA grant developed Doppler radio-controlled command systems for implanting in baboons, giraffes, sled dogs, fish, sharks, penguins. I mean, I think some of the stuff has been in National Geographic even. And so he went off into comparative animal physiology. We stayed here back at home and said, okay, all these things we've tried to do on animals, pressure, dimensions, flow, we want to do the whole thing from outside, through the skin on man. And so that became the thrust. Now, the cardiovascular instrumentation development program was a grant, individual grant. It went 3-4 year periods, was evolved into a program project grant. And it was cardiovascular instrumentation development, or instrument development for short. And so the direction shifted, and we decided that, well, obviously we can't implant anything in people, and the transit time flow meter doesn't fit anymore. So that device, I don't know if anybody ever fooled around with it anymore, but it sort of faded from history. And we started the Doppler world. Now this happens to be a picture. I have this radio at home. This was the first Doppler receiver we had in 1958, and we actually were able to pick up in a crude form of telemetry. We had a dog running around the room with a little backpack with an exciter on it for the Doppler transducer, and I could tune in at 5 megahertz and pick up the Doppler signal across the room. And he said, wow, that's a glimpse of some opportunity. So I think that kind of excited Dean, and of course he went on and do a lot of interesting, that's another whole set of stories, of course. But now, we went through evolving many types of Dopplers. And part of the problem was that there were no transistors at this time were noisy, and the signals were so feeble, and we were just learning how to do it, that we couldn't build a good Doppler thing other than with vacuum tubes. And at that time there was a very small vacuum tube called a Nuvistor, which most of you probably never ever heard of, but it could be in a museum somewhere. Anyway, because they took a lot of power and high voltage, you end up having to operate them off a wall outlet power. But we could never get the 60 cycle hum. So what we decided we really wanted was a transistorized handheld Doppler. Now Rushmer, he says, what I really want is to be able to stand up at a podium and demonstrate flow, just like that. And that was the problem that he posed to us. And so fortunately, at about this time, Fairchild Instrument, which I think is the forerunner of Intel, developed the silicon planar transistor, the 2484, which is an extremely low noise device, which I think at the time actually was classified, but we happened to get some, and we were able to build a very low noise. I spent 3 months designing a low noise receiving amplifier, which was in the probe of this unit here. And 2 of these were built, and I believe one of them is still, you still have it, yeah. This one, I actually have it at home right now, but it's been back and forth in the Smithsonian, and it will be there in the future. In any event, that was the door opener for a lot of Doppler applications. And as I say, we went on to build many different types and so on. And this was really the beginning of Gene Strandis' career. He got interested in these, and he was at the VA at that time, and used these various Dopplers, and he had his own little program going over there too. There were other people, Gene Hokinson, and I think Fran McLeod, who was another historical figure in ultrasound, also spent some time over there. But the original Dopplers came from our lab. Now, Doppler, as it was early applications in medicine, got its roots really from sonar in the Navy, where the sonar technicians listened to the sonar echoes. The signals were so complex that it was better, I mean, the mind was the best processor available. And that was true also in medicine, and it is still true in many ways. So spectrum analyzers and doing fast Fourier transforms and things like that were not possible in a clinical situation. And there were some analog spectrum analyzers, but we developed a very simple one, which we called the time interval histogram, which basically measured the interval between each zero crossing. It took the reciprocal of that, and this dot pattern at the top really is the Doppler spectral pattern. It doesn't give us any information about the intensity of the various components, but it was the first sort of spectrum analyzer, and this was on the early ATL units. Now, while we were moving forward in the vascular area, there was increasing interest in applying Doppler techniques on the heart. And if you attempted to use a continuous wave Doppler, it had no range resolution. It picked up everything in the field of view along the beam. And so we see here, for example, a vein and an artery combined together. And CW worked good in a peripheral vascular application where you didn't have other moving structures. But you could put it on the heart, and you could hear valves clicking, you could hear wall motion and so on, but you couldn't separate them. In spectrum analysis, we just got a huge mess of things. You couldn't do that. So that led to conceiving of the pulse Doppler. Now, the pulse Doppler, I got an idea about that really by, I happened to run into an article on studying the motion of snow and raindrops in clouds using a pulse Doppler radar. And I said, oh, we need to have that for our application here. Well, there was no precedence for doing this in our situation. And so we had to really develop everything from scratch. And so this really is a diagram that shows the basic concept. It was a phase coherent pulse Doppler in which we had a reference frequency, and we could transmit a sample of that into the tissue and then compare the relative phase, which give a phase modulated signal at the particular depth of the vessel, which we could range gauge, and we could know now where is it coming from and how fast is it moving. We could also tell which direction it's going. This also gives us the possibility of getting position information by getting echoes off of the structures that are there. Now, this is the first pulse Doppler. It's a bread box type of thing, and we built each section as we went along and put it all together. And this one also has been in the Smithsonian for a couple of years, and I have it at home too, but it's going to go back as they kind of shuttle back and forth. The problem with them is they don't have room to set up all these exhibits. They got more stuff than that. But anyway, these eventually, there's an early ATL unit in the background. Now, this was a 5 megahertz pulse Doppler, and we went on to build 3 megahertz and so on. Now, this is a model of the velocity profile from a femoral, a dog's femoral, and time is on this axis. This is diameter, and the axis coming up is velocity. This was done with a postdoc, Michael Nasser, from Beirut, Lebanon. back in '67, and from this point we begin to realize that with the pulse Doppler, and the sample volume size was on the order of a millimeter. So one had spatial resolution sufficient to start thinking about mapping structures and so on. And interesting as a side thing here, this model has been proposed as a master for an award that might be given by the Society of Vascular Technologists to their members, to have a trophy, so to speak, that had historical significance. Now, these next two slides are some work which a lot of time was spent on with Chuck Miller, another postdoctoral fellow who is now in the physiology at CSU in Fort Collins, using the pulse Doppler on an exposed abdominal aorta and femoral of a dog. And here we see almost a plan view. This is looking anterior posterior. And this is a plot of the velocity field at the instant of peak flow. And you can see the flow coming down, and in the dog there's a caudal artery comes off here that goes to the tail. That was closed off. And so here we see the flow making the turn. And then here is the instant of peak reverse flow. You see flow coming down each femoral, and actually, if you had this in 3 dimensions, you'd have an annular flow in the middle, which we didn't go beyond this point. It was more of a demonstration and a confidence builder for us to show that we could map things like this. And at this time, there was a lot of controversy about fluid dynamics in 3 dimensions, and Wormersley was a well-known person in the mathematics of all that, but we never got involved with that. Now, as we were evolving towards the human application situation, we began to define our thoughts came into focus on how we could characterize cardiovascular function in periphery and so on. And here we have a little drawing that says we can characterize disease in terms of vessel dimensions, tissue characteristics, flow patterns. Now, there's no pressure in this because there's no way to non-invasively measure pressure yet. Given confidence by the resolution and the kind of flow profile maps that we were able to make in experimental animals, we thought we should be able to make an image of blood vessel using Doppler techniques. And this is kind of a schematic of the first pulse Doppler imaging system, in which the transducer is attached to an instrumented arm, and then it can be moved freely, and then at each point in the vessel where we detect flow above a certain velocity, we could record a point and thereby create a velocity map. Now, here is one of the first done by Gene Strandis et al. Back in '72, and this is a femoral from a person. Here's the X-ray. You see the long axis of the femoral and the branches here, and then here's even cross sections. These are crude, and you have to realize that each dot on there represents a cardiac cycle. This is a single gate pulse Doppler, and it took some time to do this, a very tedious process. Here we see, with analog flow waveforms, a carotid, internal, external carotid, and it sort of went on from there. I'm not going to talk any more much about peripheral vascular for the moment. Meanwhile, back at the ranch, so to speak, we're looking at the heart and trying to decide, well, how would we characterize the heart? What sort of things would we do? And here we see, using Doppler to get flow patterns. Now, two-dimensional echo and M-mode echo, we did not initially get involved with because we were flow people and we didn't have any imaging experience. And that's when Jack Reed joined the program in the late 60s. And he brought the echo M-mode knowledge that he had acquired in Pennsylvania and with Wild, if any of you have ever met him. But anyway, Jack brought, and that was the main reason that Jack joined the program, is to bring in the imaging thing so we could fuse that with our flow knowledge, because we come from the flow world. And so these were melded together, which we'll get into shortly. But this was, I don't know if this was ever published. This is a flow image of the arch of the aorta with the transducer right here in the sternal notch. And this was done by Jim Cole, Steve Johnson, and Craig Hartley, who is at Baylor, I think. The first cardiac echo Doppler system consisted of a SmithKline echo system here, which did M-mode, and that was the gold standard at that time. SmithKline instruments. Now, I forgot to mention that we did a technology transfer with SmithKline in the early 60s, and they produced a CW called a Doptone. And they owned an ultrasound company called Branson in Connecticut. And that was a brief encounter that SmithKline had with the instrument world. And that was a commuting technology transfer back and forth across the country like weekly. I decided never again. Here's a later version of the pulse Doppler in a cardiac version and some other equipment. Now, I'm not sure, but I believe at this time Honeywell was just developing the fiber optic visicorder. And I have a feeling that is number one from Honeywell. Because they brought it out on a special trip just to try it out, see if we could record M-mode and so on, and it ended up in this rack. We went on then with the Jack's input in a series of graduate students. These are various mechanical rotor scanners. Number one was developed with Jack Reed and George Tomei, who was from American University in Beirut, came here to do I think, master's thesis. And you can see the three transducers on here that we go over the vessel, one pointing directly in an angle here to try to take care of the specular reflection characteristics of the vessel. Frank Barber, a later student, came in, took this on here, and so on. And we'll go on here. And here is a block diagram of the first duplex scanner by Frank Barber. And this shows the rotor transducer pointing down into the vessel and the various block diagram of it, and a very early combined imaging of tissue and flow. And so that was the beginning. And this was not simultaneous flow with imaging. You did the image and then you did the flow. You have to remember, no arrays yet. And until the array technology developed, you really couldn't easily do simultaneous flow and imaging. We explored many different types. Here's a cardiac duplex scanner with a sector scanner on the left transducer and then a steerable Doppler transducer on the right. This one never really went far because the acoustical window for looking at the heart is really too small to try to fit something like this. This is Duplex Scanner 2. This happens to be Ron Daigle, who I think went on to be heavily involved with ATL and Sonosite. And here's the rotor scanner. This was designed by Frank Barber. Duplex Scanner 3, which was a later version. And the rotor is in here, and we developed a silicon boot for coupling into the carotid, and then the Doppler transducer is aimed in here. The little knob here, you turn that and adjust the range gate so you could go back and forth into the vessel. Now, we were running against another need, and that was how are we going to combine a tissue image with a flow image? We had no scan converter technology or knowledge, so I was a good friend with Fritz Thurstone, who was at Duke University, and they were in a kind of an international competition with Jan Sommer in Holland over development of phased arrays. Well, part of their project was to develop a scan converter. And so they developed a digital scan converter for their black and white images. And one of Fritz's graduate students, David Phillips, we were able to recruit here. So he brought, we had technology transfers, intellectual transfers from our university colleagues. And so we went out and recruited wherever you see, and they said, well, come to Seattle, we'll have a good time. And Dave Phillips, Mark Iyer, listed here, his father was a cardiologist here in Seattle, and he was a very bright engineer, and they put together a totally digital scan converter in which we could see these color images. Now, this is the real beginning of the color flow, and on the left we see a long axis of the carotid. This is a venous valve flapping here. Here's an image with the overlaying flow image. Once again, you got the tissue image, and then the flow image was laid over that. And this image here is a Valsalva maneuver done by Marco Brandestini, who was another engineer who came from Swiss Federal Institute in Zurich. And he developed the multi-gate circuitry for the pulse Doppler. And if you're familiar with the Valsalva maneuver, you take a deep breath and you hold, well, you release the breath here. This is the carotid, this is the jugular vein, and here's a bolus of venous flow, and so on. And so that starts to give you a little idea of the potential. Closer up, this one I think has actually been on the cover of a bioengineering publication. Well, now I'd like to take the last 20 minutes, 15 minutes, and talk about technology transfer. Now, Rushmore had a philosophy along the way, and we frequently had what we called show and tell meetings, presentations. We were accumulating a lot of knowledge and information and methods, which we felt, or he felt, I think, that local industry, or maybe not local, but industry, should take an interest in. So we would show things, and they would come, and occasionally there would be interest. But in November, I think it was, of 1973, Howard Susskind and Ralph Estango, Howard Susskind was the founder of United Control Corporation, which became Sunstrand, and he became financially independent out of that, and he was sort of an entrepreneurial godfather. Ralph was an engineer of a company that United had acquired, and he'd help his engineers to start new companies. So they came over here to the university and said, we have an opportunity to develop an ultrasonic emulsifier for emulsifying cataracts of the eye. What do you think about that? Well, I happen to know some people at the Wills Eye Hospital who had actually been involved in the development of it. And I said, what about this? Well, they weren't very enthusiastic at the time. So I came back and told Howard and Ralph, I said, well, I don't think there's a future there for you, but we have a tremendous collection. I referred to it as a bolus of knowledge that we have been accumulating for many years in the instrument development program. And I said, why don't you consider getting into ultrasound? And over about a 3 or 4 month period, and a lot of this was done right at my kitchen table over in Kirkland. So, see, have to realize, no ultrasound experience, no medical experience, all they had was an interest. And people would ask me, why did you go to them? I says, I liked them. As simple as that. And so we taught them, and Joan, my wife, is also involved in ultrasound, and so we taught them medicine and ultrasound and got them involved. And Ralph was a kind of an engineer who really got into things, and he learned enough so he could carry on a conversation with a physician, which, you know, for an engineer takes a little while to do, all the terminology and so on. So anyway, the first ATL unit, which we transferred schematics, and they were over in Evans Industrial Park in Bellevue at the time, and 2 people. Ralph, his wife, was the bookkeeper, and they had 2 or 3 contract engineers, Boeing type, you know, traditional engineers, I'd say. They were good engineers, but they had no sense of that. So they built, and this is the first one, which was shown at an ultrasound meeting here in the fall of '74, and it went from there. Here is a couple generations later, combined echo Doppler. One of the things we learned early on was that the Doppler was too far ahead of the field, the pulse Doppler. Medicine didn't know what to do with this information, and so we had to go. It was just as if we had gone to an island offshore and nobody could see where we were. So we had to go back to the beach, said we got to build a better M-mode echo than SmithKline. And that's what we got an engineer from Applied Physics who developed that pulse echo system, and then we eventually wed them together. And here you can see the rotor scan head. This was the ATL version of it. And the first duplex scanner, 76, 78. And our program project grant was not refunded in 1978. And so the program disbanded just like that. We had about 40 people, and it was just not possible to continue. So it took me about 2 years to get over that. But I went to Squibb Medical Systems at ATL and started becoming faculty for the world, I guess. And so my main role at this point now was to teach people throughout. I've been on every continent in this world, and in many countries and in many situations. And I would organize seminars, multidisciplinary, and this happens to be, this was one that was put on here in the United States in 1982 in all these various areas. And we had to create our luminary group. We had to go out and identify the best cardiologists, the best vascular people, bring them up to speed. They did research, we worked with them, and they become the hosts of local seminars. And so we would bring in a few people. We would assemble a traveling faculty along with the local host, and it worked very well in the Western world. It didn't work in the Soviet Union. That's another story. But anyway, we still penetrated the Soviet Union and had our Dopplers all over there too. But people saw this as an opportunity. It's the same story again. The war is fought according to the weapons you have. They saw an opportunity to get ahead of their colleagues and publish. And so it was a good thing for them to get involved, whether it was France or Holland or Middle East or South Africa or whatever. Well, let's ask the question, did the vision come true? In many ways it did. If you say, well, Russell's vision was to characterize the cardiovascular system in engineering terms, to make measurements transcutaneously through the skin and take it to the world, I would say yes, we probably succeeded more than we realize. Here is a list of the major companies in the world now who sell echo Doppler. It's standard equipment. You don't buy an ultrasound machine anymore without it. And ATL, you see there in the top. Now, they were acquired by Philips a couple of years ago, and in the process is a merger with Agilent, which is a spin-out of Hewlett-Packard. And so they represent 27% of the market. Acuson, Siemens, ATL was unable to put together a color flow imaging project within their company structure due to internal politics. I helped try to reorganize the company to do it. But so what happened, so it couldn't happen internally, 3 people left ATL, formed Quantum in Issaquah. And that was the first color flow peripheral vascular. And they brought in another group of Boeing engineers who were interested in fast Fourier transform, in arrays and so on. So that was a new surge of technology came in. Well, Siemens, after a while, bought them and moved their world ultrasound headquarters to Issaquah. So now all of the ultrasound for Siemens is there, and they've now acquired Acuson. GE, I knew some of the people in the early days of Dialsonics. I don't know. Vingmed is an offspring of the Trondheim Technical Institute in Trondheim, Norway, with Bjorn Angelson and Liv Hatley, which developed CW Doppler techniques for looking at the heart, and a company emerged in Norway called Vingmed, and eventually GE bought that. And the others I don't have a lot of knowledge of, but that gives you an idea. Who does this? Sonographers are the people that do the ultrasound procedures, and they are the most knowledgeable group doing it. I mean, there's a kind of little turf war goes back and forth between them and the physicians, but there are some 11,000 diagnostic sonographers. By the way, my wife was the founder of both of these. ARDMS is the American Registry of Diagnostic Medical Sonographers. They are the credentialing agency for the people that do this. And estimated are over 100,000 people doing ultrasound. These are purposely trained sonographers as well as on-the-job training people and so on. How big is the market? Well, this is the amount of money spent on these various medical imaging procedures. And this is not very old. This is only a month or so old. But ultrasound is a $3 billion in the U.S. CT 2, MRI 2, nuclear 1, and general radiology 1. 800 million ultrasound procedures globally per year. It has clearly become the preferred, most cost-effective diagnostic modality. Well, what didn't happen, at least in my view? While we started to look at non-invasive measurement of pressure, we never quite got there. We did We were able to measure pressure using an ultrasound beam remotely in water. But when it come to blood, there was a total vacuum of knowledge, nothing. And that's where it's left. I don't think quantitation evolved as much as it might have. It has certainly evolved. Medicine is so oriented to imaging and what you can do by looking at things that quantitation has a little different significance. We did get involved with a project with Gene Stranis, and I think Dave Phillips got involved with looking at the features of the Doppler spectrum and so on. Now, the mind does great things in analyzing these signals and looking at the images, but there's a lot of opportunities there, I think, for that. And one of my wife's pet things is ergonomics. There's a tremendous amount of injury in the field amongst sonographers from the repetitive nature of the scanning and so on. And so there's opportunities for this ergonomic design of instruments. Well, what might happen next? Well, some of you probably are better acquainted with this than I am, but miniature handheld scanners, as you're starting to see emerge in the local area, ultrasonically introduced and activated drugs, so on 3D, digital image manipulation and display, you know, sort of the ultrasonic walkthrough of the body kind of things are all out there. I had an engineer who sometimes felt like he was pressed a bit hard. And he created this, which we named Wylers Law. You know, and you can, not impossible for the one that doesn't have to do it. I think everybody can relate to that. And finally, thank you very much. That's my landing craft that I play with up in the San Juan Island. That's going to a family reunion picnic over on Stewart Island in the San Juans. Thank you.